Today I want to prove a result for twin primes. And 3 and 5 are the first two twin primes. 3 is prime, and then 3 plus 2 is prime. But notice that 3 can't be congruent to 5. Okay, it's basically because 6 is 2 times 3, so 2 and 3 kind of are exceptions here. So we want to prove that when you divide any twin prime, the first a prime of any twin prime, that it's always going to be congruent to 5. Okay, so that's why it says n is greater than or equal to 5 here. Okay, now let's move along here. There's a very important lemma. Any prime, and p is understood to be a prime here, leaves a remainder of 1 or 5 modulo 6. Now another way of stating that is p is equal to 1 plus some multiple of 6, we'll say 6k, or it's equal to, p is equal to 5 plus 6k. Right. These are the equivalent standard ways, if you want to call it that, of stating what we mean by this modular arithmetic statement. Okay, in other words, it leaves a remainder of 1 upon division by 6, or a remainder of 5 upon division by 6. Okay. Now let's just go ahead and take the time to prove the lemma, and the rest of the proof is fairly easy. When you divide any number, not just any prime number, by 6, you get a remainder of 0, which would be the case right here. A remainder of 1, a remainder of 2, a remainder of 3, a remainder of 4, or a remainder of 5. That's exhaustive by the division algorithm. Now notice right here, p is not a prime. P would be a multiple of 6, so this wouldn't count. Okay, in other words, 6 would divide p, which means it's not a prime, right? 6 divides p right here. Now, that's equivalent to saying p is congruent to 0 mod 6. Now right here, no problems right here. This is a possibility right here, but notice right here, p would be divisible by 2. So we'd have to rule out that case. Right here for this particular case, p would be, what do we have here? 6 divides p, and then right here we would have 2 divides p. Okay, again, y'all, I'm saying p is equal to either 6k, 6k plus 1. Okay, now right here, in a similar fashion, 3 divides p. Again, meaning p can't be a prime. And right here, 2 divides p. So you can see the only thing that is left over are these two cases, 6k plus 1 and 6k plus 5. So that proves this lemma, a proof within a proof, a very useful proof. So we're trying to show that the very first of the prime, twin prime, has to be congruent to 5. That's what we're trying to prove right up here. N has to be congruent to 5. So we're going to do a kind of a standard proof, contradiction proof here. We'll assume that p is not congruent to 5. Okay, well that only leaves one other possibility, that p is congruent to 1. But notice that if you add 2 to both sides, you get p plus 2 is congruent to 3. And you see, folks, this would be our contradiction, because remember, p plus 2 is posited to be a prime, because it's the second one of the twin primes, right? So this is prime. It's a prime number that this supposition has led, that has created this condition, a prime number congruent to 3, when we know it can only be congruent to 1 or 5, right? So this is contradiction. I'll just put contra abbreviated. Not anything to do with Iran. That's abbreviated. Okay, and so that completes the proof. Now, let's look at a few examples here, just believability, So proof is completed. So let's go back up just to some examples. We've already shown you that 3 and 5 can't work, but notice that 5, the very first twin prime checks, right? 5 comma 7, check, right? 5 is trivially congruent to 5 mod anything, right? Now let's look at the next. What's the next one? 11 and 13. Okay, so we can see that 11 is congruent to 5, right? It's the first one, right? You can prove more with this. I'm just proving the first one. This also proves that the second one has to be congruent to 1 for the next multiple up. Okay, but 11 is congruent to 5, of course, mod 6. What's the next one? 17, 19. 17 comma 19. 17 divided by 6 is 12 plus 5, right? So you see 17 is congruent to 5. And you can check all the others. I mean, well, not all of them, because it's posited, that hadn't been proven yet, that there's an infinite number of prime pairs. But 17 is congruent to 5. And let's see, what's one more we can do? Let's 29, 31. Twin prime. And 29 certainly leaves a remainder of 5. If you divide 5 into 29, you get 6, you get a remainder of 5, right? 4 times 6 plus 5. 4 times 6 plus 5, right, folks? So you can see it definitely is true. And it also proves the second one is congruent to 1. And you can think of, you'd be going the next multiple up, but it still works out, okay? So that does it, folks. Let's see here, I guess, yeah, that we completed it. Thanks for viewing.